Okay, this is the next bit of the 13F, and this is the central limit theorem. This is quite challenging, and I'm going to deal with a little proof at the start. You can skip ahead if you want, but I think it's probably worth doing this little proof. And I'm basically going to try and unpack this thing here. The reason why it's important to know this well is because it turns up later on in chapter 14 as well, or unit 14, okay? So let's just take this to start off with. Let's take this bit here. So this is where the central limit theorem is stated. And let's just go through it. Let's go for it. Okay, so the central limit theorem is this: the mean X bar of a sample of size n taken from any population with a mean of mu and a standard deviation of sigma can be modeled by a normal distribution. Okay, so we've taken from any population. Not necessarily a normally distributed population, but it can be modeled as a normal distribution with a mean of mu and a standard deviation which is much smaller, which is adjusted by dividing by the square root of n, provided that n is at least 30. Oh, there's a lot to unpack there. What I'm going to do to start off with is just try and come up with this result, and I'm going to try and do it by looking at the combining of variables. So first of all, what are they talking about in terms of X bar? So we've got X bar here, and what we're saying is let's take several observations from one distribution. Okay, let's say, let's go back to the example of the maths results. If we have everyone in the year group sitting some maths results, we might say, okay, well, let's just take a small sample of those. Let's take a sample of n, and that would give us our X bar, if you like. That's a sample mean. If we took, maybe we take 5 of these, but we take n of these, and that's dividing that thing by n. Now you can see that here we have a combination of variables. This is not transforming variables. We are not timesing the maths results by 5 or by n here. We are taking n separate results from, now they could be from different distributions, but it happens in this case that we care about the mean X bar. So it's all coming from the same variable, the same sample that we're taking from, which is not necessarily normally distributed, in fact. Right, okay. So where are we going to go from here? Well, if we wanted E of X bar, well, then we could take E of all of this thing here, but then you could take out the 1 over n, because that's simply a factor which is applying to all of these things here. You could see this as 1 over n times x1, 1 over n times by the second one, and so on. So we can factorize out the 1 over n, and we can bring that outside the front. So that's 1 over n lots of E of x1 plus x2 and so on, okay, plus xn. Okay, and now we know from our results from before that that's the same as saying 1 over n E of x1 plus E of x2 and so on. Okay, so all the way up to E of xn. And now because E of x1 and E of x2, because they all come from the same distribution, then that's, each one of those is just the same as saying E of x. So we can take all of this back and we can say that this is the same as our E of x, but of course that's happening n times over. Okay, so we've got E of x1 plus E of x2 plus E of x3 plus up to E of xn. So we've got that n times, so that, and each one of those is the same as E of x because they all come from the same distribution. And of course, these two things then cancel, which just leaves us with E of x. Well, not a very exciting result. That if you add together lots of scores, then the average is going to be, is going to be the expectation of the original distribution. Not particularly exciting, to be honest. Okay, but either way, you see the way in which this is working. So what are we really talking about there? We're talking about the mean of this. Let's just take this back. So in the statement, you can see that it's saying that the mean of this population is mu, but then the mean of X bar is going to be mu as well. That's essentially what we've shown. I don't know if I've read that back to front, but basically they're going to be the same thing. The mean of X bar is going to be mu, and the mean of X is going to be the same thing, as is the expectation. Okay, right. Now, when we talk about the variance, something slightly different is happening, of course. So when we do the variance of, again, this whole thing here, again, we can take out the 1 over n. But remember, if we take out the 1 over n with all of our results in here, so if we factorize out the 1 over n, and when we take it outside of the brackets here, then that's going to become 1 over n squared. That's what we learned in the last video. So then we've got the variance of x1 plus x2 plus all the way up plus xn. Okay, now this can be separated out. We have one lot of each of these things. So that's going to give us n lots of the variance of x1. So we've now got 1 over n squared. And then this thing can be split up using the previous rule to give us n lots, or rather the variance of x1 plus the variance of x2 plus the variance of x3 and so on. But that just gives us n lots of the variance of x, because the variance of x1 and the variance of x2 are the same thing. Okay, now in this case, you can see that it's not quite the same. So we're getting the fact that the variance of x bar, which is what we're dealing with here, that's where we're starting. Okay, the variance of x bar, which is this, its variance of this, simplifies to this, simplifies to this, simplifies to this, is giving us 1 over n of the variance of x. So obviously, our x bar statistics are going to be less spread out than the values which we've taken from the original distribution. Let's try and make some sense of that as well. So let's think, if we have, say for example here, say we have a distribution, maybe it's like a Poisson distribution, something like this. Okay, something like that. Okay, now if we're taking random observations from there, they could be from all over. Okay, so those are going to be your different random variables which you're taking from, and they're quite spread out. Now, X bar from a few of these things here would be, I don't know, maybe it's there, maybe that's going to be your result for X bar in that particular case. Now, if you did that several times over, then what does the distribution of X bar look like? So I'm trying to draw roughly the same thing here, okay? So I'm going to get, for one set of values, I'm going to get an X bar which is here. And for another, I'm going to get an X bar which is here. And another, I'm going to get X bar is here. They're all going to be much, much closer together, probably closer than that. The question is, how much closer are all of these X bars going to be? So those results here from this original distribution, all of these separate X bars which I'm taking, they're going to be much closer together. So whereas when we're talking about X, and potentially this is, I don't know, we don't know what the distribution of this is. Potentially this has, I don't know, a Poisson distribution of, let's say, 25 is the statistic there. Now, when it comes to X bar, now if we take, as long as we take n being more than 30, maybe we've taken X bar 50 times, then you're going to get out that this becomes a normal distribution. So all of these X's tend to be very close together and spaced in terms of a normal distribution. And the more of them you get, the more they're going to tend towards a normal distribution. So they're going to follow a normal distribution with a mean, in this case, still 25. And the standard deviation is going to be sigma over n. Well, hang on. What did we say the variance of X bar was? Well, the variance of X bar was the variance of X divided by n. So in fact, this is a formula I would prefer to use. So we've got here n back there. So we can see that the variance of X bar is going to be the variance of X divided by n. So in this case, we'll get 25 divided by, let's say there's 50 in the population, so divided by 50. So these X bars are not going to be spread out very much. So they're going to have a variance of a half there. And yeah, they're not going to be spread out very much. And they're now going to follow a normal distribution. And this is going to be our new variance. Now, in terms of the standard deviation, obviously, if we wanted the standard deviation of this, we would need to square root this, and we would need to square root this as well. And if we square rooted this, we get this thing here. Okay, so you could see this as sigma over square root of n all squared. But if you just want the standard deviation to put into your calculator, you can just do sigma over the square root of n. From my point of view, I remember this because I realize that these things, the variances of combined variables are connected and not the standard deviations. Okay, so the variance formula is much easier to deal with. Okay, so this is quite unusual in terms of one distribution has become another distribution when we start looking at how the means are spread out. If we had many means there, how would they be spread out? So this is quite unusual in going from one to the other. And this is still X bar, this is not Y. This is coming from the original distribution, which was a Poisson distribution. Okay, now, if on the other hand, X was distributed as a normal distribution to start off with, X was distributed as a normal distribution with a mean of 25, and again, let's say a variance of 25 in this case as well. So pretty much a similar distribution to this, but not quite Poisson, bell-shaped curve, and we're using continuous data, of course. So if we had this as our normal distribution for X, then we can immediately say that this is our X bar distribution, even if we have n is less than 30 in this case. So if we're originally coming from the normal distribution, then it doesn't matter about the fact that n has to be 30 or more. So for example, if n was 10, then this would still be valid for our X bar distribution. Okay, right. And that's because we're making E of X and variance of X from our normal distribution. Okay, well, I guess there's not been proof of that. There's just a discussion of the idea that these means are normally distributed. And it doesn't matter if you come from a binomial distribution, Poisson distribution, or any other distribution, as long as we're looking at sample means and as long as n is greater than or equal to 30, and obviously the higher n is, the better, then we can see that X bar is distributed like this. Okay, right, so let's deal with a question here. So let's deal with example 17 maybe, and then 18, 19. Let's see if we can go through these ones. So let's do 17. Okay, so Food Standards Authority. These get a little tricky now. Let's try this one out. So Food Standards Authority survey finds that the number of calories in a takeaway meal in takeaway meals from a national restaurant chain, Speed Food, is distributed normally with a mean of 1,900 calories and a standard deviation of 80 calories. Right, assume that the recommended daily intake of calories is 2,000 calories. Find the probability of the following. Randomly chosen takeaway contains more than the recommended daily intake. So what are we looking for there? The probability that X is greater than 2,000. Remember, this is a normal distribution, so we don't need to say equal to as well. So greater than 2,000. And what was X? X was distributed normally with a mean of 1,900 calories and a standard deviation of 80. So that's 80 squared when it comes to us writing down the variance. Okay, so this is really simple. That's straightforward. You can do it on your calculator. We are not talking about X bar here. Okay, I'm not going to go into the answer for that. You can check it on the calculator if you like, but it's giving us just over 10%. Okay, for part B. Now, for part B, they're saying the average calorie intake for a family of 5. Right, so the distribution is now changing. So now we're talking about X bar. we're talking about combining normal variables. We don't have to worry about the central limit theorem because this is normally distributed stuff anyway. So we don't need to worry that there's only 5 here. This is fine to use the normal distribution. It's only when we have X bar and n is greater than or equal to 30 that we can go from a Poisson or binomial distribution to this normal distribution. Okay, so normally distributed in this case, we've still got the mean is going to be equal to 1900, but now we have the fact that the variance, which was 80 squared, needs to now be divided by n, and n in this case is 5. Okay, which means that your standard deviation that you're going to give your calculator is going to be 80 over 5 square rooted. Okay, so we need to square root this thing to get the standard deviation. Remember what that was? That was the standard deviation divided by the square root of n. This is the standard deviation now of x bar. You could, if you like, call that x bar down here. Give it a little subscript there. Okay, right. So this is our new distribution, and now we're asking for the family of 5, is the average calorie intake. What's the probability that the average calorie intake is more than the recommended daily intake? So we're talking about whether or not this is greater than 2,000. Again, we're still asking, is it greater than 2,000? Now, obviously, we're expecting this to be much closer to 1900. This distribution is going to be much closer to 1900 than the original spread out distribution of one family. Okay, which could be more like this, sort of spread out normal distribution, flattened, because we can see that the variance has been divided by n. Okay, right. So let's have a look at the answers for this one. Again, you can just use your calculator in this case. We can see in this case we're getting less than 1%. In fact, about a quarter of 1%, 0.26%. Okay, so the conclusion to this one is that the mean calorific content of 5 meals is far less likely to be above the daily limit than the calorific content of a single meal. This is due to a smaller standard deviation of the sample mean. Okay, right, so there we go. That's example 17 done. So example 17, just to reflect on this, this specifically said that we had normally distributed information to start off with, which enabled us to combine variables. That is, we combined the meals for 5 of the members of the family, and therefore we could combine them. And it meant that the expectation or mu was going to be the same, but the variance needed to be divided by the size of the sample. Okay, right, so let's have a look then at example 18 and example 19, and I think I'm done with this video. So let's do example 18. Let's check this one out. Okay, so this one says the number of emergency calls per hour to a hospital between 9:30 a.m. and 10:30 a.m. each day follows a Poisson distribution with a parameter of 6.3. So we're saying X is Poisson distributed with 6.3 as our parameter. Okay, so we also know that not only mu, or actually lambda is representing both the variance and the mean in this case. So mu is 6.3 and the variance, so sigma squared, is also equal to 6.3 here. Okay, so use the central limit theorem. So fortunately they're pointing us in this direction. So central limit theorem here to find out the probability that in 40 days, so X bar is going to be normally distributed, 6.3 is the mean. In 40 days, we're going to have 6.3 divided by 40 there. That's going to be our new distribution here. So what's it saying again? Find the probability that in 40 days, the mean of the number of calls between 9:30 and 7:30 is less than 5.4. So we're taking 40 observations we're adding them together essentially and dividing by 40 to get this mean. So n is 40 in this case, 40 observations. There we go. We can go straight to this. Okay, so this is an example of where the central limit theorem is possible. It's also possible because n is greater than or equal to 30 as well. Let me just check that I've got the right size here. That we're still dealing with 6.3. Yeah, it's talking from 930 to 1030. Yeah, okay, there's no scaled up version of the Poisson distribution there as well. And we're finding the probability that this is less than 5.4. So we need probability X bar, so this from this distribution is now less than 5.4. Okay, now again, we can go straight to our calculator. We can go normal CDF. We can put in this information. Remember, of course, that sigma is going to be equal to 6.3 over 40 all square rooted. Okay, because this is sigma squared in this case. Okay, let's just check the answer to that one. So they're saying the answer is just over 1%, 0.0117 there. Okay, right, so let's do example 19 and we're done. You can get some practice with the questions. So example 19. So we've got scientists are comparing the growth of two types of wheat. Type A has a mean height of 23 centimeters and a standard deviation of 3.1 centimeters. Type B has a mean height of 22.5 centimeters with a standard deviation of 4.1 centimeters. Okay, so we've got, perhaps we can call that X and Y, or why not, let's call it A and B. Okay, let's call it A, distributed then with a normal distribution 23, standard deviation of 3.1, so 3.1 squared there, and B is normally distributed with 22.5 and 4.1 squared. Okay, so find the probability that a sample of 50 blades of wheat taken from type A has a mean of greater than 24 centimeters. Now, A here I'm letting represent the height of one grain of wheat. Is that right? Mean height and standard deviation. So yeah, no, that's fine. That's fine. So okay, so A is representing any piece of wheat. Okay, find the probability that a sample of 50 blades of wheat. Okay, so now we're saying here A bar is going to be equal to, again, 23 and then 3.1 squared divided by 50 there. So for this one, we're looking for the probability that A is has a mean of greater than 24 centimeters. So we've got A bar is greater than 24 centimeters. What's kind of stalled me slightly here is when we talked about the mean height here, that's they're talking about mu there in that part. That's the population mean they're talking about. It's the population of this wheat. And here, when they're talking about the mean, they're talking about the mean from the sample. So it's just stalling me a little bit when I looked at this question to wonder whether or not they were originally defining A bar or whether they were defining A. But since this was a population mean that they're talking about, and here they're talking about taking a sample. So now this is where we're talking about A bar in this case. So they're sort of using mean in two different senses here. There's both mu and X bar. So this is population mean they're using in the first case, and the second case sample mean. Okay, so again, this is straightforward now using your calculator. Just of course remember to use sigma is equal to 3.1 over the square root of 50, or in other words, this thing square rooted. Okay, and for part B, let's check the answer to that. So you can check it on your calculator as well. So there we go. We can see your answer is 0.0113. Very similar answer to the last question from 18. And then let's look at the second part here. So part B, we've got find the probability that a sample of 50 blades taken from sample A has a greater mean than a sample of 50 blades taken from sample B. Oh, okay. So here we're saying what's the probability that A bar is greater than B bar. Okay, so that's the same as, we can use the same trick as before on this one, where we could take these to one side. So A bar take away B bar is greater than 0. And then we're obviously going to need to combine two distributions here as well. Now we have A bar, we need B bar here as well. We now need to combine two already combined distributions, if you like. So here we've got 23, no, not 23, 22.5, comma 4.1 squared over 50 is the variance of this one. So now we're going to need to combine the two distributions of A bar and B bar as well. So in that case, we'll have the expectation of A bar minus B bar is nice and simple. That's going to be now that's going to be the 23 take away 22.5. I think it's also helpful the fact that we have 50 in both of these cases as well. Otherwise, we might actually have to do E of 50 lots of A minus. It could get complicated. I think they've been generous in giving us 50 in both cases. Okay, so we can do the 23, take away this one here. I wonder if I'm wrong on that. No, it should be good. I think it's actually should be good combining these two distributions, whatever, because I think, well, let's not go down that rabbit hole just at the moment, okay? so then we need the variance, obviously, in this case as well. So the variance of A bar minus B bar, and then we can combine these two, of course, by doing the variance of A bar, and then plus minus 1 squared. So in other words, just plus the variance of B bar in this case as well. So now that's going to give us our normal distribution, whatever you want to call that X if you want to. So you can call this variable here X. And so now you can say for the variance of X in this case, hey Bella, I'm just finishing off a video here, yeah? Bells? Doesn't care. Okay, so then X is going to be the same as, if you like, X equals A bar minus B bar. So that's going to be distributed with a mean of 23, take away 22.5, and a variance of this plus this. I'm running out of space here. Let's have a look at what the book's doing. So it comes up with the distribution for Y. It does exactly the same thing. It's also calling them X bar and Y bar in this case. No, I called them A bar and B bar. Getting tired here. Right. There we go. There's the normal distribution in the last case. I've called that something else. I called that X. I said X is distributed normally like this. But there we go. We've got this. Now we just want to know when is this variable, when is Z, if you like, greater than 0. We can just use this normal distribution given above in order to complete this on our GDC here. We should get the probability of 75%. Okay, I'm done. I'm done, and you can hear that my wife is back from work as well. Okay, there we go. So have a go at exercise 13F. That's the last one in chapter 13. This is good to get good at because the central limit theorem also turns up in unit 14 as well. Okay, thank you very much for listening.